All right. Well, today we're not going to do any theorem proving, so I don't even think I'm going to bother having the equation sheet up on the screen. Instead, today what we're going to do is we're going to apply what we've learned to two problems. Okay, so here we have two problems, two applications. We have an in-house joke here. I'm going to crack up. Two applications. Okay. Okay. First application is this. What we want to be able to do is, given a program, in other words, if we have a specification and if we have not a specification, if we have a precondition and a program and a postcondition, we want to be able to prove that that is correct. Okay, so the first problem is proving correctness. So, given a program, prove it satisfies its specification. Prove it satisfies its specification. All right? And the way we prove this, well, I'm not going to show it on the board, but the way we prove this is with p.19. What is p.19? You have your equation sheet there?
It is.
Anybody?
To show that x gets E is an implement of precondition Q, x gets question mark, postcondition R. Prove Q implies R with x substitute.
You know, I should have. Now I see that I should have shown this, but it's the only one that we need to show to see. So I think I'll not bother to show it on the screen.
I could have it still pop up.
Yeah, we can do that. All right. So p.19 is specifies how to. Yeah, let's take a look at that and show it on the screen. Okay. All right. So that's the first problem. Now the second problem is kind of an interesting problem. It's going backward from what we have been doing so far a little bit. Okay. And what this is given an unknown expression, given an unknown expression. No, this is what's interesting. In an assignment, solve for the expression. Solve for the expression. And basically, this is sometimes called program derivation because you are deriving the program itself. All right? So this is an interesting problem. It's interesting that you can actually do this with formal methods. Okay? So we're going to do both of these. We'll start with one, then we'll do some examples of two after that. All right. So this one is sometimes this is called proving correctness, and this is called program derivation. Okay, these are the terms that are used in formal methods literature. All right, so first of all, let's do proving correctness. So here's one, proving correctness. And we're going to do this by example, with an example. And our example here is to prove the following. Int x, y. This is going to be a very trivial one, super trivial. Okay, and the precondition is y equals 1, and then we're going to do x comma y gets x plus 1 comma x plus y, and then the postcondition is going to be x is greater than or equal to y. All right. So now notice that we're not solving for the weakest precondition or anything. What we're given here is we're given the fact that x and y are integers, and we're saying this is the precondition, and these are the statements, and this is the postcondition. So what's the interpretation of the Hort triple? If the precondition is true and you execute the statements, they will terminate, and the postcondition is guaranteed to be true. Okay, so now if you look at p.19, that gives us a recipe for how to prove this. Okay, and what does P.19 say? What is it that we have to prove? We have to prove that what does it say we have to prove? If you look at P.19, let's look at P.19 again. We'll have your P.19.
Implies that
The actual precondition does what?
implies the postcondition with
Implies the weakest precondition. Yeah, which is we know how to do that with assignment.
substitution.
Right, okay.
This is kind of like what we did at the very beginning of the year.
It is. Okay, so,
Not this year.
what we did there is we calculated the weakest precondition. And we know how to calculate the precondition, but now the way we use it is we have to prove that the actual precondition implies the weakest precondition. Do you see what I'm saying? So here, let's write this out. So here's what we must prove. Must, by P.19, okay, so by P.19 must prove, so let's just write down what we must prove. We must prove that what?
Y equals 1.
That y equals 1 does what? Implies,
X greater than equals Y with X higher than
yeah, let's just write it as weakest precondition dot, are you with me?
yeah.
X comma y implies x plus 1 comma x plus y dot what?
X greater than
X is greater than or equal to y. Does everybody see that? Is everybody with me on this?
So the
By P.19, this is what,
But P.19 is R with X replaced by E. Is that the same thing as the weakest precondition? Because that's what it says in P.19.
well, that's what this is. It took it's once, are you with me? If we calculate the weakest precondition of this dot this, that's what that will be.
We're by P18. That's what
By P18. Oh, yeah, good point. By P.18.
Yeah, because that's what I was asking.
Right. See, yeah. P.18, yeah.
This is perfect.
This is good. So does everybody see what we... So with this, what we're going to do is we're going to start with the right-hand side and get it to follow from the left-hand side.
Okay.
Are you with me?
Do it.
Okay, so here we go. So here's the proof.
P18.
So we'll start with this. WP dot x comma y gets x plus 1 comma x plus y dot x greater than or equal to y. And say it again, which one? Equals by what? P.18 tells us how to calculate this with an assignment.
P18 and textual substitution.
Yes, and T, yes. Might as well. P18 and textual substitution says, okay, so now,
X plus 1 is greater than or equal to X plus Y.
yeah, so x plus 1 is greater than or equal to x plus y. Are we good?
Okay.
So equals by some math, right?
Y is less than or equal to
Equals by math.
or 1 is,
So,
1 is greater than or equal to Y.
yeah, or another way to say it, 1 is greater than or equal to y. 1 is greater than or equal to y. Now, you guys,
Does Y equals 1 imply? Y is
yeah, good question. What are we trying to get? We're trying to get this to follow from y. So here's my question. Follows from, now what do we claim, what do we hope this does? Follows from this, what do we want this to follow from?
Y equals 1.
Y equals 1. Now, is this true by math?
I don't think so. I mean,
Wait a minute. Does y equal 1 imply y is less than or equal to 1?
well, it definitely implies because half of it is equal. Like part of the.
Okay, here, let me ask it, hold,
The other way.
no, but this, hold it, if we go from here up to here, then we're doing implies. If we go from here to here, we're doing follows from, right?
I know, I'm
Can you,
saying,
can
So
you
here's-
put it out on the line?
Here's my question. Here's my question. Does y equal 1 imply y is less than or equal to 1? In other words, scratch paper here. Y equals
The only
1
way for it to be no is
implies,
y equals 1 can be true and y is greater than or less.
if this is true, then is this necessarily true?
Yes, that's it right there.
oh. Yeah, you're right.
Are you with me?
Yeah, I just don't like it.
You just don't like
And
it.
is that by math?
Yeah, by math, because we know this is, we're talking about properties of integers here, less than or equal to equals. Are you with me? So this, boom, that did it. Is everybody?
And that's true in all states, because if that's false, then it doesn't matter.
Yeah, exactly. So we know that because y equals 1 implies, so does everybody see how so therefore this is correct. Therefore this, we prove that this program is correct. Okay?
Now for that first application, will we usually do that? Take the right-hand side and follow from the right?
Yeah, yes, this is how we will always prove program correct. Okay, so let's do another one. Okay, okay, so now here we have another one. Int x, this time we'll just have x instead of an x and y. And we'll have precondition x equals 5, statement x gets 2 times x plus 3. These are just nonsense programs. X gets
Nonsense.
2 times x plus 3, and then the end postcondition will be x equals 13. And this is just a trivial program just to make a point. All right? So now, by 3.19 we must prove blah, 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 blah. So what do we start off? We start off with,
Can we go,
What's
can we
our-
go straight to the proof?
yeah, let's go straight to the proof. Let's go straight to the proof.
WP.
So
dot
WP,
yes.
yep. WP dot, so what is this going to be?
Oh, that. Okay.
So what is this?
2x
2x plus 13. Or sorry,
2x plus 3, not plus 13.
ah, making all kinds of mistakes here. Okay,
Equals 13.
yeah, so this is 2x plus 3 equals 13. And this equals by math what?
X equals 5.
310. X equals 5. But now what do we have to get it to? To do
Follows
what?
from x equals 5.
Follows from. Now how do we
By
get it?
some theorem that says P implies P is P.
Well, which one? Which one? Oh, which one is it?
371.
371.
We can't use it that way, right? If P implies P is true.
Oh. Well, yeah, which means P implies P.
Which means
But-
P follows from P, which is true.
Right.
So we can do that.
Yeah. The true is redundant there, right? Yeah? Does everybody see how that works? Okay, so this is this is,
With this technique, do we have to, it can follow from or just be equivalent to,
well, it could. I mean, if you know,
so that's kind of a superfluous step.
yeah. But I mean, technically,
It can be equivalent to because of that.
yeah. This is a stronger, I mean, getting it to equal it is a stronger, but we can, anyway. Are we good? Does everybody see how to do this now? So this is pretty straightforward. You're given the whole thing, you just want to see if you want to prove that it's correct. So this is how you prove that a program is correct. Now, here's what's interesting. The interesting thing is the second one. Now watch this. Here's the idea. The idea is that if you don't know what one of these things is supposed to be,
Okay.
you can just make it like an unknown expression, E, big E,
Okay.
all right? And then what happens is you go through all of this, and in order for it to be true, you get an expression for E. And that way you can calculate what your assignment statement has to be in order for the program to work correctly.
Let's try it.
You see what I mean? So it's what's given. So it's what's given. Now what happens is we have an unknown in our assignment statement, And we're going to solve for and we can actually solve for the unknown. In other words, we can actually calculate what what has to be in our program. It's called program derivation. Okay, it's pretty slick. So this is an example of two. Okay, deriving expressions. Well, I mean, it's going to be.
You have to know some of it?
Well, you have to, yeah. Well, you have to say what you have to do is you have to say, well, I know that I want to assign this to something. So you have to kind of like know which. You have to have an idea of what variable needs to be assigned to, right? But then you don't know what to you don't know what to assign to it. So you make that the unknown.
So is this the first like practical thing we're doing?
Well, this is everything that we're doing is practical because it helps us to think
If we wanted
correctly.
to write a program and we knew what we started with and we knew what we wanted to end with, we could do this to figure out how we get there.
Yeah, you could. All right, so check this out. So here's our example for this kind of problem. Solve for unknown E. Solve for unknown E. Capital E is an expression in the following. So watch this. So here what we're going to say, we have int x, and our precondition is going to be true. Now this here is a super trivial example just to show you the mechanics of how it works. Precondition is true, and we're going to say x gets some unknown. I could put question mark here, but this E is like the question mark. Are you with me? And then in the end, we want x to equal 4. Now obviously. Exactly. I mean, in order for this to work, x would have. But let's just show you the mechanics of the steps of how you would go about in a more difficult. And then, well, actually, here's what we're going to do. We're going to start with what is this? This is a what?
Hor triple.
It's a Hor triple. We're going to start with a Hor triple.
Before?
Yeah, we're going to start with the whole thing. So we're going to do we're going to do true x gets E, x equals 4. Now equals by, yes. Because that's the definition of a Hor triple. So what would that be?
True implies.
So that would be true implies, and then this is going to be the weakest precondition. Dot x gets E. Oops. X gets E dot x equals 4. All right. Well, what about this true implies? We can handle this right away, right?
3, 7, 2.
Ooh, very close.
3?
Yeah.
It's 3, 7, 3.
You guys know your numbers. Okay, so true implies P is just P, right? So this equals WP dot x gets E dot x equals 4. Okay?
I thought we always assumed the conjuncts on this one.
Oh,
Are you lying?
I lied.
So we don't assume the conjuncts.
Well, we will. Yeah. Okay, so this equals by P, yes, good. P.18 equals by P.18.
X equals 4 with x replaced by
And TS.
X equals 4
With X replaced
with X replaced, now watch this, with X replaced by what?
E.
E. Okay,
E equals 4. Ha.
and then equals by textual substitution. So equals by textual substitution, E equals 4.
Done.
And we're done. Okay, so,
All the slashes.
well, we're not really proving, well, whatever.
Oh.
We're not really proving this is true, we're solving for E's. So anyway, so what we have then is this. We have true, let's just write out the program. So the program is true, x gets 4, x equals 4. Now, obviously, this is trivial, but it shows the steps that you have to go through in a more complicated. Okay, so now let's do something more complicated. We're going to do a little segment from what's called the division algorithm. Okay, so watch this. Solve for unknown e in the following. Now check this out. It's a little more complicated. 0 less than or equal to x and 0 less than y. Okay, so this is saying that x is non-negative, y is positive, right? Are you with me?
Right.
Okay, and what we're going to have is q comma r gets q comma r gets e comma x. Now q stands for quotient and r stands for remainder. Are you with me? And in the end, here's what we want to have. What do you know is a property of the remainder? The remainder is always positive, right? You know, like if you have one integer, like if you have 13 divided by, okay, so 13 divided by 2, the remainder has to be either 0 or 1. So it has to be, well, in that case, it's 1. So what you want to have happen for the remainder is you want the remainder to be 0 less than or equal to r. In other words, it can be 0, but it has to be positive, right? And what we want to have, so we want this, and we want q times y. Sometimes I use dot, sometimes I use asterisk, because we're doing GCL, it's kind of like a program, you know, for multiplication. So q times y plus r equals x. Now, do you see why this has to do with division?
Yes.
Because q is the quotient. So what we're trying to do is we are setting q and r. Oh, I forgot to give the types here. I'm going to squeeze it in. Int. Our int is x, y, q, r. X, y, q, r. Okay? So what's changing in this program? What's given and what's changing? What's given? X and y are given. And it's given that x is greater than or equal to 0 and y is strictly greater than 0. Right? That's given. And we want to set q and r to e, and we want to set r to x and q to e, and we don't know what e is, in such a way that 0 is less than or equal to r and q times y plus r equals x. So you see, if q is the quotient, then we want q to be the number such that if you multiply it times y and then add the remainder, you get x. Does everybody see that? Now we're going to do. Now I'm going to write down what I said before but had to erase. So what must we have here? Now let's yeah, but you know, because of the Hoare triple thing, what must we have because of the Hoare triple? We must have what? This does what? Implies that. And now we're going to have some conjuncts. We're going to have two different conjuncts. Are you with me? So now we're going to, so here, we must have 0 less than or equal to x and 0 less than y implies weakest precondition, WP dot q comma r gets e comma x dot 0 less than or equal to r and q times y plus r equals x. All right, so now we're going to use the technique of assuming the conjuncts of the antecedent. So, technique, assume conjuncts of, is that 4.4? I'll take your word for it. All right, so now what we'll do is we will start with this, and anytime we go through here to get it's you know, we want to work our way towards solving for e. We can assume any of these conjuncts as we go, right? All right, here we go. WP, so here, where do we start? WP dot what? All right? So obviously equals by what?
We can do P2, or we can split the.
Well, let's go ahead and do it. Let's go ahead and do it. What do you mean split?
Well, it's the conductivity, because we have two.
Oh, I see. No. We don't need to do that. We'll just do
So
it.
we'll do P18.
Yes. P.18. Oh, I see what you mean. Conjunctivity. Hadn't thought about that before. So what will this be? What is this? What do we have to do? We just write this down, and everywhere there is a what? Everywhere there is a
Q, we get
Q
okay, so
here,
0
and everywhere there's an R
and X.
and X.
So 0 is less than or equal to X.
So it's 0 less than or equal to X,
And
and
E times
That's
Y.
y plus x equals x. So e times y equals 0.
yeah. But what about this conjunct? What about this 0 less than or equal to X?
That's true.
Yeah, we assume, the way we notate this is we assume conjunct 0 less than or equal to X, all right? So if we do that, what do we get?
Just E.
We get true and, well, we could skip this. Well, I've started, I'll just go ahead. You could, yeah, E times Y plus X equals X
339.
equals by 339.
Identity of
And math goes by 3.39. And math, because what can we do with this math? E times y plus x equals x. Subtract x from both sides. True and this is just this, right?
E times Y equals 0.
And then, yeah, so we get E times y equals 0. So equals by more math. What? E equals 0. Okay? So the program is,
Oh, because Y can't be 0. Nice.
yes. Oh, that's a good point. Actually, that's a good point. Math, and because y cannot be 0 by what?
Because y is greater than 0.
Math and, yeah, we should note that. Math and conjunct, yes. Math and conjunct y is greater than 0. Because otherwise,
Y could.
why couldn't y be 0? Yeah, that's a good point. So the program is int xyqr, and then it's 0 less than or equal to x, 0 less than or equal to x, and 0 less than y, 0 less than or equal to x, and 0 less than y. And then the statements are actually qr gets
0x.
and then 0 less than or equal to r, and q times y plus r equals x. Yeah? Are we good? Okay, well, let's do some more. We are just going to keep on trucking, and we're going to do more complicated examples. Next one is going to be one where we have a sequential. Okay? Because this was simultaneous, right? But you know, like if you're dealing with Java or C++ and these languages that don't have simultaneous assignments, okay? So let's derive some sequential computations. Derive sequential. You know, it's a good, well, they're older languages. I mentioned before that there's a language, you remember what it was? There's a language that does have it. A new, no, Pascal is very old, it doesn't have it.
We started Ruby in operating system.
Yeah, I'm not sure if Ruby has it or not. Yeah, and Python is what I'm thinking of. And it's actually, that feature it would be very nice if more modern language, if languages did this, because it's much easier to prove correctness. When you have sequential, when you're limited to sequential computations, they're more difficult to prove, and they're also more difficult to think about. It's really a nice feature. I predict that all modern languages from now on will probably have it, because that seems to be the trend, you know. So int. I think also Mathematica. No, I might not. I don't remember. You know, Mathematica is a. Okay, so let's do this. Let's say that our pre is this. It's x equals rigid x, okay, and y equals rigid y. All right? So we're defining what the initial values of x and y are. And now we're saying the program is going to be x gets e semicolon y gets x plus y, all right? And in the end, what we want to have happen is we want x to equal the original value of x minus the original value of y, and we want y to equal the original value of x. All right? So the problem is solve for e. Oh, wait, yeah, solve for e. So problem, solve for e. In other words, what must you set x to if afterwards you're going to do y gets x plus y, and in the end you want x to be the difference of the original values, and you want y to have the original value of x. Does everybody see what the problem is? And this e is unknown. Now, here's the thing. X and y, rigid x and rigid y are rigid variables. That means that they cannot appear in E. Are you with me? You can't, you can't, you can't put a rigid variable in your program, because a rigid variable just defines what the initial value of this variable is. So you don't have access to it. You don't necessarily have access to it. See what I mean?
Yeah.
Okay, so rigid variables, as a general rule, rigid variables cannot occur in E. Okay. Now that's different from constants. I think we had an example before where we had a and b, and those were const int. Remember, we had a const int thing. Those can. It's legal for them to, but not for rigid variables. Okay. So we'll do.
Could you not make your own rigid variables within the program in the same kind of idea?
The rigid variables occur in the precondition. That's where they are defined.
Okay. Yeah. Yeah.
Are you with me? So, well, you could have some other variables in your program and define them however you want. Yeah. Yeah.
That's all.
Yeah.
So do we start with P.4 again?
Yeah. Let's go ahead. Let's not. At this point, we know that we're going to use the Hoare triple. The precondition implies the weakest precondition, and we know that we're going to do the weakest precondition, and we know we're going to assume the conjuncts of the antecedent. Are you with me? So let's just go ahead and, so what we'll do is so here's the, this has to imply blah, blah, blah. Okay, so I think we can skip all that stuff. So let's go ahead and, at this point, so let's go ahead and do weakest precondition. See what I mean?
Okay, right.
We can, all that stuff's always the same, so let's just do WP dot, now what? Now what's the program here? What's the process here?
X gets E.
X gets E, semicolon, Y gets X plus Y, dot,
0. Oh, X equals. How do you?
this, rigid X. X equals rigid X minus rigid Y, and Y equals rigid X, right?
Yeah.
So X equals rigid X minus rigid Y, and Y equals rigid X. Okay? So equals by what? P.18 and textual substitution.
E.
Well, actually, No, actually, it's not quite right.
We have to split them up first.
Yeah, we have to split them up. Well, because of this.
With the composition.
See, it's not because of this, it's because of this. Yeah.
14.
Is that, what is that?
That's composition.
So is that P.14? So this is going to be what? WP dot
X hits E.
X gets E. And now it's dot, and now it's the what?
Weakest precondition.
It's the WP dot
Y gets X plus Y.
Y gets X plus Y dot this, right?
Yeah, the whole.
X equals rigid X minus rigid Y, and Y equals rigid X. Boom, boom. Yeah? Are we good? Are we good? Okay. So, okay, so this equals by what?
Now can we do P18?
Yeah, now we can do P and TS on this, right? P.18 and TS on this is going to be what? So we carry this down. WP dot X gets E dot. Now how do we do this? How do we do this? We have to take this, and everywhere there's a what?
There's a rigid variable.
No. Everywhere there, we write this down, but everywhere there's a what?
Y.
A Y, we replace it with
X plus Y.
X plus Y. So where are the Y's here?
Just on the right.
Just here. So this is what?
X equals rigid X minus rigid Y.
Rigid X minus rigid Y,
X plus Y
and X plus Y
equals rigid X.
equals rigid X. Is everybody good?
Then we do P18 and TS again.
And now we do P18 and TS again, equals by P.18 and TS again.
E.
And so now everywhere there is we just write this down, and everywhere there's an X, which now occurs in two places because of,
Right.
yeah, huh? Okay, so everywhere there's an X, we have to replace that with what?
E.
With E. So what is this? Everywhere there's an X, you replace it with E.
E equals rigid X minus rigid Y.
E equals rigid X minus rigid Y,
And E plus Y
and E plus Y
equals rigid X.
equals rigid X. Oh my goodness. Now what? Oh, how can we solve this for E? We got an E over here, we got an E over here. What resources do we have at this point?
Like
How do we,
assume the conjuncts.
what about the conjuncts?
Assume the conjunct.
Yeah, so we assume, what are the conjuncts?
X equals rigid
X,
and Y
X equals rigid X, and Y equals rigid Y. Okay, so what's,
Just insert them.
yeah, so what is this going to be? E equals what?
X minus
X minus Y.
X minus Y, and
E plus Y equals X.
E,
plus Y, leave it there. Or do you want
E,
equals X?
yeah, okay, so, all right, so we'll do E plus Y equals X. But E plus Y equals X is the same thing as what? E equals X minus Y. So what is E equals X minus Y and E equals X minus Y?
E
Not
equals X
true.
plus Y. It's itself.
What property is that?
Weakening.
No, it's
P and P is P.
yeah, that's what it is.
Yeah, what property is that?
Idempotent.
Idempotent. Right?
338 idempotent.
Idempotency of and, right? Give me the number.
338.
338. So what is this? E equals X minus Y. So that's what it is. Right? We solve for E.
We did.
Now we have to do the code.
Yeah, so the code is, so the program is program
E gets x minus y.
is
Int x, y.
is x equals rigid x and y equals rigid y. And then it's x gets what?
X minus y.
X gets x minus y, semicolon, followed by
Y gets x plus y.
y gets x plus y. And then we know that in the end, it's guaranteed that x will equal rigid x
Minus rigid y.
minus rigid y,
And y
and y
will equal rigid x.
will equal rigid x. Right? Are we good? Okay, we're going to end this video recording with a description of a technique that you need to use in the special case where you have two assignment statements executed sequentially, not concurrently, but sequentially, and the unknown expression is in the second assignment statement. And we're going to illustrate it using this example for calculating the next pair of Fibonacci numbers. So you see the whole triple that we have here. In the precondition, we have x equals rigid x and y equals rigid y. And then we want to execute the two assignment statements. Y gets unknown expression e, and then semicolon, which is the sequence operator in the guarded command language, followed by x gets unknown expression f. And in the end, we want x to equal the original value of y, and we want y to equal the original value of x plus y, because obviously the Fibonacci number, the next Fibonacci number, is calculated as the sum of the previous two Fibonacci numbers. Okay, so how do we perform this computation? How do we derive these expressions? We use deduction, 4.4, like we did in the previous examples, and we start by computing the weakest precondition of the two statements dot the postcondition. And so the first theorem that we use is the definition of composition, which is P.14. And so if you look at what P.14 is, what happens basically is the weakest precondition of the second assignment statement is the postcondition of the first assignment statement. And so using P.14, this expression equals the weakest precondition of y, of the statement y gets unknown expression e, and then dot the weakest precondition of x gets the unknown expression f dot the postcondition. And then, as usual, we do, because of the assignment statement, we use the assignment statement P.18 and textual substitution. Now, what is the next line going to look like? Well, what you have to do, remember, is you take the x equals rigid y and y equals rigid x plus rigid y. And everywhere there is an x, you replace it with f. So we bring down the weakest precondition dot y gets expression e. And then the postcondition with everywhere there's an x, you replace it by f. Now what we have is the weakest precondition of y gets unknown expression e dot f gets a rigid y, and y gets rigid x plus rigid y. Now here's where the problem comes in, because you see f is an expression, and it may contain variables. And so now what happens is, when we take the weakest precondition of the statement y gets unknown expression e dot this postcondition now has f in it, which is an expression which may contain x and y. So we're going to use P.18 again, right? But now what happens is, everywhere in the postcondition that there is a y, you have to replace it with uppercase e. But here's the thing. There is obviously y appears in that postcondition in the expression y equals rigid x plus rigid y, but y might also occur inside f. So whenever we do this step, not only do we have to replace the y with the big E in y equals rigid x plus rigid y,
but we also have to replace y with e in the expression, unknown expression, f. So you see, because f is an expression and it might have y in it. And so we have to take and so remember, f with the superscript y and the subscript e is an abbreviation for f with y replaced by e. So that's why we need that. Here's where this is where the complication comes in, because we have our unknown was in the right assignment statement, and so it needs to be textually substitution when we do the textual substitution of the first one. Okay, so now how do we go? Where do we go from here? First, we assume the conjuncts x equals rigid x and y equals rigid y. So that means we can replace the rigid x and the rigid y with x and y respectively, okay, in the expression. So that gives us the following. So this is the same. So we bring down the f with y replaced by e, and then we have y and e equals x plus y. But now what do we do? Well, and here it might not seem obvious what the next step is, but there is a previous theorem substitution, and we've written it out here in this next step. It's 3.84a substitution. And what happens is, if you have an expression where you have e equals f and you have e with z replaced by e, then that's the same thing as e equals f. So you can just bring down the e equals f and e with z replaced by f. How do we use 3.84a? Well, the little e in 3.84a corresponds to the big E in what we have, and the little f in 3.84a corresponds to x plus y in what we have, and the little z in 3.84a corresponds to the y in what we have, and the big E in 3.84a corresponds to the big F in what we have. So how do we apply 3.84a? Well, we bring down the E equals x plus y, and then in place of the big E in what we have, we replace that with x plus y. So consequently, the next line is f superscript y subscript x plus y equals y, and then we bring down that E equals x plus y. Because after all, if it's basically this is substituting equals for equals, right? Now, so what do we have so far? So let's go to the next slide, and we'll start with this last line of this slide. So now, what have we calculated? We have solved for one of our unknowns, E, big E. We know that big E is x plus y, but what about big F? But how do we figure out the expression capital F? Well, it is an expression such that if you replace y with x plus y, that has to equal y. So you kind of have to work backward to do this. So here's how it works. Working backwards, you should be able to deduce that f must be y minus x. Now, how do we get that f is y minus x? Because it has to satisfy the fact that if everywhere there's a y, you replace it with x plus y, you get y. So here's how it works. It is f equals y minus x, because if you take f superscript y subscript x plus y, that by definition is f with y replaced by x plus y. Well, if you do that textual substitution, what do you get? You get y minus x. Everywhere there's y, you replace it by x plus y. So what do you have? You make the substitution, and you have x plus y minus x. But what is x plus y minus x? By a little math, x minus x is 0, and y plus 0 is y. And so you have y. So that's why f must equal y minus x, because if you take f and everywhere there's a y, you substitute with x plus y, you get y. So you kind of have to work backward to do this. You have to sort of, it can be a little tricky at times, but it's usually simple to do, and you have to use logic like that to do this, to solve this kind of a problem. So the final program is y gets x plus y, and x gets y minus x. Now you can see that this works by an example. Recall that the Fibonacci numbers, two of the Fibonacci numbers are 3 and 5. So suppose you have the state of the computation has x has the value 3 and y has the value 5. And what happens if you execute that program? Well, y will be 3 plus 5, so that makes y 8. What is x? Well, x is y minus x, but now the new value of y is 8, and the current value of x is still 3, so 8 minus 3 is 5. So the final values of x and y are y equals 8 and x equals 5. So they are the next two Fibonacci numbers. Okay, so in general what happens is you have to be careful, because if you are doing a program derivation and you have two assignment statements, and the second assignment statement has an unknown expression in it, you've got to make sure that when you do P.18 and textual substitution, that you consider that expression f, that unknown expression in the second assignment statement might have some variables in it, and you have to explicitly put those variables in there when you make that step, and then deduce what that expression is at the end of the process. Okay, so that wraps up this example.
Should we call it quits?
Yes.
All right.
Nice day.
Sports fans, that's it.
How many fans?